This month's Where Did the Road Go is sponsored by Allison Cook and Super Inframan. Thank you so very much. And now our show.
Transmission start. Welcome to Where Did the Road Go? Join us as we wander off the path and explore lost history, consciousness, the paranormal, unexplained mysteries, alternative thought, and much more. We are present on the web at wheredidtheroadgo.com. Now here is your host, Seriah.
Welcome to this edition of Where Did the Road Go? And tonight I am joined again by Randall Carlson, and it has been a while since I've had you on, Randall.
Well, it's been too long, Seriah.
It has.
I don't know what's going on here.
Well, a part of it is you're not associated with Sacred Geometry International anymore. And you wanted to make that clear to everyone.
I'm not. I've moved on, and I am now simply people want to find anything that I'm up to or new material or old material. It's just randallcarlson.com.
Okay. All right.
So,
and that has all your stuff on it?
No, at present it doesn't, but it soon will.
Okay. And it has
anything new for sure is on there.
And that includes your new podcast with the Snake Brothers?
Yes, it does.
Okay, and that's Cosmographia?
Yes, with a K. Cosmographia with a K. Cosmographia podcast. We are talking mostly about global change right now in its various manifestations. We just had Jerome Lessman, a geologist from the Vancouver Island University, and we were talking about Drumlins, these mysterious elongated hills that seem to be associated with glaciers in some way. And Drumlins have a very interesting story to tell. But I don't know if you want to get into that tonight, but that's something I've been really engrossed in for the last few months. We're planning to go this September to do some exploration of drumlin fields, but under the circumstances with the COVID and all that, it became too complicated. So yeah. I'm postponing it till spring.
Yeah, hopefully we'll be in better shape by the time spring rolls around.
Good gosh, I hope so.
So there's been a bunch of stuff I want to talk to you about, but one of the things that I've been and was on the top of my list, and one of the things you've been talking about a lot is the Younger Dryas period. And currently, I think we talked about it the very first time you came on, which was, like maybe 5-6 years ago at this point. But what do you think happened at the end of the last ice age?
Well, to me, it was a series of events that we're still figuring out. But it does appear that it involved an encounter with some type of a cosmic object, most likely a disintegrating comet nucleus. The imprints of the encounter are very diverse and have led to some of the critics and the skeptics dismissing the idea simply because the evidence does take such a diverse set of forms that are really quite remarkable in their own way, because they're the signature of something that let's put it this way: you're trying to identify. You say, okay, the Earth encountered something, so it must have left fingerprints. Okay, we want to investigate those fingerprints to try to identify the culprit. Problem is that the fingerprints are so diverse, it almost looks like multiple culprits. And because of that, the skeptics were, and still are, and probably rightfully so, questioning the veracity of the claims that something like that happened. But the problem is that there are so many convergent lines of evidence and research that have no explanation in isolation. But when they converge into a single phenomena, then they start to make sense. For example, the mass extinction of the megafauna that were so dominant in the Pleistocene epoch, and right down to the end of the Pleistocene between 12 and say 14 or 15,000 years ago, when all of unglaciated North America, which was roughly in the east of Mississippi, roughly below Chicago and southward, and what is now the southwestern part of the United States, was all non-glaciated, and was a very different environment than now, and was inhabited by this amazing bestiary of these mega mammals, the mastodons, the mammoths, the giant beavers, the ground sloths that were the size of elephants, camels, dire wolves, saber-toothed cats, huge bears, Ursus spalaeus, the cave bear, Artotus simus, the giant short-faced bear, and the list goes on and on and on. So by the time you get to the end of the list, you're talking about over 100 species of mega mammals. Most people don't understand. If you look at North America, non-glaciated North America during the end of the last ice age, and you try to look at the density of the large mammalian population, if you then go to try to find modern analogs, probably the closest you're going to get is the Serengeti Plain of Africa, because Africa at present has one species of elephant. Now, get this: North America had 4 proboscidean species during the Ice Age. Four different species of elephant: the Columbian mammoth, the Mammuthus imperator, the imperial mammoth, the mastodon, and the most famous of all, the woolly mammoth.
Right.
So, proboscideans being creatures with long snouts, long noses. So as I get older, I've noticed myself becoming more proboscidean-like. So yeah, you see, you got the rapid disappearance of those animals. Now the argument is, were they all killed off in one single instant, or was it spread out over several thousand years? The answer is either way. It's a very complicated and challenging problem to solve.
Yeah.
How so many large species of animals became completely extinct. Okay, now the other thing is that during this same short-lived period from about between 15,000 and 11,000 years ago, we could narrow it down even a little more than that and say from about 14,600 to 11,600 years ago, during a 3,000-year window, the climate of the planet went through these enormous changes and swings, these oscillations back and forth between, warming and cooling and warming again. Sometimes those swings amounting to as much as 15 degrees Fahrenheit is in as little as 3 to 5 years. In some cases, maybe even in a year or two.
Yeah.
So this is inexplicable. But clearly, to me, if these kinds of climate changes are going on at the same time, we're seeing this spike of species mortality in the animal kingdom, well, wouldn't it seem like there's a connection? Then, on top of that, we have the megaflooding sequence, which appears to have begun between, around 14,500 to 15,000 years ago, and was pretty much over by, say, 11,600 years ago. But in that period of time, you had the full deglaciation process, which meant that you had to convert something like 6 million cubic miles of ice back into water and return it to the ocean basins. So before the melting of the Great Glacier Complex that existed during the end part of the Pleistocene, sea levels are, you got a picture, 400 feet lower.
Right.
Now, when you drop the sea levels 400 vertical feet, think about what happens to the coastlines of the continents. They migrate seaward. Mm-hmm. And in some cases, that migration may be a dozen miles, and in some cases up to 50, 60, 75 miles seaward from where those coastlines are now.
Yeah.
So as the ice is melting and sea levels are rapidly rising, what it's doing is it's drowning several million square miles of coastal shelf that were exposed during the peak of the Ice Age. So now you got that. You've got this melting. Now, the problem there is it takes energy to melt ice. And we simply run into a problem of physics that was first identified really in the late 60s and early 70s. And the problem is this. First, old assumptions. Old assumptions were that you had 30, 40, 50,000 years to get rid of that much glacial ice, right? Because what you're doing is going, okay, well, most of that glacial ice was over Canada, right? So if we look at the climate at that time in that area I mean, literally, Seriah, was like that of the South Pole. Because the South Pole is the only, of the Earth today, is the only place where we can find a ice mass equivalent in scale to the ice mass that covered North America at the end of the last ice age. To sustain that much ice requires basically a polar climate. So we've got this polar climate that has prevailed over half of North America, whose only modern analog is the South Pole, Antarctica, right? Now, 6,000 years later, that's gone. And we have the climate that's there now. Now in Canada, in the winter, yes, indeed, it gets cold and you get a lot of snow. However, come spring, the snow melts, the melted water goes into the overland stream system and into rivers and back to the ocean, or it goes into groundwater. But in either case, there's a hydrological cycle going on where during the warmer temperatures, the water is evaporated from any water on the planet whose surface is exposed to the atmosphere. That water is evaporated. It goes into the atmosphere. It circulates. It precipitates back out as rain or snow. Now, the way the climate is today, for example, in the winter, you'll have a collection of snow. Where I grew up in Minnesota, you had 4, 5, or 6 feet of snow by the time you got to the end of February. And then, of course, spring came and all that snow melted away. Now, if we're going to reduplicate the ice age, basically what we do is we flip a switch and we turn off the hydrological. What we do is we put the hydrological cycle on steroids, and we ramp up the amount of water being evaporated, because in order to increase the rate of precipitation, you have to increase the rate of evaporation. So now you're precipitating a whole lot of snowfall over half of North America, and at a very high rate. And then instead of spring coming, spring doesn't come for the next 15,000 years. And then by the time you get to 15,000 years of accumulation, that ice is 1.5 miles thick in the middle. Right. And it's swallowed up 7 million or so square miles of the Earth's surface. Now you come to about 13 to 14,000 years ago, and spring does come. And when it comes on, boom, it comes on very fast. So now you have the mega melting. You have this massive scale of melting. And the problem was that the scientists, that mostly the geologists and glaciologists, realized in the early 70s was this. Old assumptions was that if you had, how long, if we look at Canada today, right? Let's say it snows, then in the spring the snow melts, right? But here's the thing. If you're going to accumulate that amount of snow each year and then get rid of it, it's going to take energy to get rid of it.
Yeah.
Now, if you took the climate of Canada today and you buried it under thousands of feet of ice, and then you were going to have that ice sit in the climate of today, because it's not going to be melting during the winter, is it?
Right.
It's only going to be melting in the summer. So now, how long is it going to take to melt away, 5 or 6 or more million cubic miles of ice? And the answer is a really long time, Seriah, like tens of thousands of years.
Right. I heard I heard the equation that even if it had been moved to the equator, it still wouldn't have melted down as fast as it did.
That is exactly right. And this was the energy paradox that was first identified in the early 1970s and spawned a couple of international conferences that didn't resolve anything other than the fact that hey, wait a second, we used to have the comforting concept of tens of thousands of years, and then radiocarbon dating came along, and we discovered that, hey, there were forests growing in Canada, where the ice was 1.5 miles thick. 20,000 years ago, 30,000 to 35,000 years ago, there were forests there. So on both ends, everything got accelerated by a couple of orders of magnitude, really. So we have to figure out the mystery of how you convert a planet from an interglacial, such as we're in now, to a glacial, and then get it back out again, and do that whole cycle within about 25,000 years. It's a very, very challenging problem. So we have the megafaunal extinction. We have the massive megafloods that were a consequence of this rapid melting, this hugely accelerated melting. Now we're talking about megafloods that are measured potentially in hundreds of millions, maybe even billions of cubic feet per second. Now, to throw out a number like that is going to be meaningless to most people. But then you have to start trying to visualize what we're talking about here. If we talk about just the flow that was measured, let's say, in northeastern Washington, roughly in the region of Spokane, Washington now, where one of these giant meltwater, because that whole valley, the Spokane Valley, if people want to ever look on Google Earth or on a map, you can see Spokane, and you'll see it sits at the southwest terminus of a valley that reaches up into Canada, right? Well, during the melting, that valley was carrying discharges of water that peaked out at about 750 to 800 million cubic feet per second. Okay, so now to get a picture of that, you have to imagine taking every single river on Earth. Now, I mean, you start thinking about all the rivers in North America, South America, Africa. You know, we're talking about the Mississippi, we're talking about the Columbia, we're talking about the Ohio, we're talking about the Mackenzie, the Colorado. In South America, it's the Amazon, and in the Africa, you're talking about the Nile and the Congo, and we could go on and on to the great rivers of Europe, the great rivers of the Yellow River in China, these huge rivers, right? Now, if we take all of the rivers, and we throw in all of the creeks and streams and everything, every bit of flowing water on Earth today, put it all together, it's going to be somewhere between 1/10 and 1/20 of the water flow that came through that Spokane Valley. And that was only an isolated example. So, and most people are completely oblivious to the kind of, to the knowledge of that has now emerged about this planet we live on and some of the things that happen to it. So we have the megaflood. We have the rapid climate change, right? We have the megafaunal extinction. And now what is happening is that when we get to bring this all back to the Younger Dryas, is that we have this boundary layer that is known as the Younger Dryas boundary. And in dozens of examples around North America, this boundary layer is indicated by what's called the black mat. Now, the black mat is a dark, carbon-rich layer, sometimes an inch, sometimes 2, 3, 4 inches in thickness. And typically, below it, you find extinct megafauna remains, but never above it. Now, there's another factor we got to throw into the mix, the Clovis culture. Now, the Clovis culture was this, I'll say mysterious culture that showed up around 13,400 years ago in the archaeological record of North America. They were very widespread over a very short period of time. They were identified, by their unique spear points and tool kits and the residuum of their cultural occupation of non-glaciated North America. And then around 12,900 years ago, as mysteriously as they appeared, they were gone. I mean, apparently completely gone. So what happened to them? That's an interesting question. So you've got archaeologists looking at the mystery of the sudden rapid appearance and disappearance of the Clovis culture. You've got paleontologists looking at the rapid extinction of the megafauna and trying to explain that. You've got glaciologists attempting to explain the rapid disappearance of the glaciers. You've got climatologists attempting to explain these massive swings, repeated swings, oscillations in global climate, up to, like I said, 15 degrees Fahrenheit, which is
a lot.
Basically, it's a lot. It's 15 times greater than the amount of warming since the beginning of the Industrial Revolution. When we look at, assumed global climate in the mid 19th century to now, we're talking about a degree to a degree and maybe a degree and a half. I think a degree centigrade, so that would be about 1.8 degrees Fahrenheit. So it's many times greater than the modern warming. Okay, so you've got climatologists looking at that, trying to explain what is causing these massive spikes in cooling and in warming. You got the archaeologists trying to explain the rapid disappearance of the Clovis culture. I guess I mentioned that. But then you've got the hydrologists, or I should say paleohydrologists, who are attempting to explain the cause of these gigantic megafloods that swept over large portions of the Earth's surface repeatedly at the end of the last ice age, and undoubtedly gave rise to the many legends found all over the Earth about world-destroying floods. Because once you understand a flood of 500 million cubic feet per second, you would understand easily that somebody who somehow, by the luck of the draw, managed to survive such an event could easily assume that the whole world had been destroyed.
Right.
You see, so here we have all of these questions that have arisen around this unique period that is the transitionary phase between the Pleistocene and the Holocene, right? The Pleistocene epoch and the Holocene epoch, which essentially means the whole region, which is now given as from us now sitting here at this moment back to 11,600 years ago.
Right, right.
So now we go back to this interesting and kind of mysterious black mat layer that has been associated with a couple of things. Oh, the other thing I mentioned that the megafauna remains are typically found below it, but never above it.
Yeah.
Well, the other thing is that the Clovis occupational evidence is always found below it, but never above it.
Right.
So this Clovis culture, the Clovis people, whoever they were, wherever they came from, at that horizon, right there that marks the final peak extinction episode of the megafauna, they're gone too. That also coincides with a huge pulse of warming and a huge pulse of meltwater into the global oceans. So in looking at that layer, what they did, Richard Firestone, I think he was out of Berkeley Livermore Laboratory back in 2007, published a paper in which they presented the results of their inquiry into the nature of this black mat layer.
Yeah.
And it ignited a firestorm of controversy that's still going on. The paper was entitled, and here it is. This was Richard B. Firestone, Alan West, James Kennett, and 23 others. So 26 scientists contributed to this paper, but the lead author was Richard Firestone. The title of the paper, Evidence for an Extraterrestrial Impact 12,900 Years Ago that Contributed to the Megafaunal Extinctions and the Younger Dryas Cooling.
Yeah.
So that was the first barrage of what I had already come to believe had to have been part of the explanation, maybe even 15 or 20 years before this.
Oh.
And the evidence that, they looked at this layer. I'll just read a little bit from the abstract here. A carbon-rich black layer dating to 12.9 Ka. That's K for 1,000, A for annum, which means years. So 12.9 Ka would be 12,900 years ago. It has been previously identified at 50 Clovis age sites across North America and appears contemporaneous with the abrupt onset of the Younger Dryas cooling. So that was one of these big climatic spasms where it went from warming to sudden cooling,
Right.
Basically in an instant. The in situ bones, which means on-site bones of extinct Pleistocene megafauna, along with Clovis tool assemblages, occur below this black mat layer, but not within it or above it. Causes for the extinctions, Younger Dryas cooling, and termination of Clovis culture have long been controversial. In this paper, we provide evidence for an extraterrestrial, or ET, impact event at 12.9 Ka, which we hypothesized caused abrupt environmental changes that contributed to YD cooling, major ecological reorganization, broad-scale extinctions, and rapid human behavioral shifts at the end of the Clovis period. So they looked at sites, let's see, in Michigan, Arizona, New Mexico, Alberta, Canada, South Carolina, Belgium, California, I guess, the Carolina Bays they looked at in South Carolina. So they drew from quite a wide variety of sites, which, since this was published in 2007, about 7 other teams, independent of the original team, have gone and taken a closer look at that particular horizon, the Younger Dryas boundary.
Yeah.
Let's see, Mexico, Venezuela, the Italian Alps, Syria, even Antarctica, several other places. And what they're finding is that at that horizon that dates to 12.9 thousand years ago is the markers of this, what is most likely some type of an impact. But the nature of this impact is very mysterious, because it's not, the culprit is not easily identifiable. And like I said, it almost appears that there were several culprits acting in tandem. Now, there's a couple of other things that's a possibility too. This is dating at 12.9, right? 12,900 years ago.
Right.
But you had a massive melting spike at 14,600 years ago that really started the whole process. And then you had another, in fact, at 14,600 years ago, the meltwater spike has been actually given a name. It's meltwater pulse 1A, where, and this was independently identified by oceanographers and marine geologists who could find evidence from where the sea level was at its lowest point during the late glacial maximum, and how it rose quite rapidly, relatively rapidly, and then stalled for a while, long enough to leave a remnant shoreline. But this remnant shoreline is like 300 and some feet down below the modern sea level.
Right.
And the transition time between these I'll say oceanic still stands was very rapid. So, and that would make sense when you shift from a marine environment to a terrestrial environment, and you find you've got these evidence of these gigantic megafloods, which clearly implies massive evidence of something is triggering huge amounts of melting. And then you've got, at the same time, other independent scientists going, hey, there was a very rapid sea level rise at this time. So that would all make sense that these things would fit together. So the question is really comes down to the nature of the culprit.
Right.
What happened? And see, I like to distinguish between, when you're trying to do a forensic analysis of a crime scene, you look at invisible stuff like fingerprints that you can only see with technological enhancement. And then you've got the more macro scale evidence that might be like the footprints, right? The footprints in the yard that somebody, left the crime scene, right? You can actually see those. So what this work going back to 2007 is, it was like the discovery of the fingerprints. And the megafloods, that's clearly like footprints, because you can actually look and see the stark evidence of these gigantic, intensely erosive events that have stripped away, oftentimes hundreds of feet, sometimes 1,000 feet or more, literally of bedrock, stripping it away and transporting it 50 or 100 miles away and then dumping it. Right. And in the tours that I take people on, we look at that. We go and I show you, I'll take the example of Grand Coulee in eastern Washington. It's 52 miles long. There's an upper coulee and a lower coulee. And in places it varies between 1 mile wide and 5 miles wide, and it's typically around 800 to 1,000 feet deep. and it's ripped right out of bedrock, basalt bedrock.
Oh.
And at the south end of the 52-mile coulee, which is basically like a canyon with no flowing water in it at present, you find splayed out over a couple of thousand square miles a boulder field that's billions of these boulders, basalt boulders, that's all the wreckage and rubble that's been stripped out of creating the canyon, the coulee, and there it is splayed out. And if we had visuals, I could be pulling some of this up so you could see it. But people, if they go to my website, they're going to be able to see all of the things I'm talking about. Because this is what we've been doing for the last 25 years, is documenting this stuff. So
and that's randallcarlson.com.
randallcarlson.com, yes.
So
the Cosmographia podcast, I mean, we've gone into great detail into the evolving evidence regarding these events, and of course, it's profusely supplemented with video clips and imagery and things like that, so that people really can see what I'm talking about.
Right. Right. So, but basically, what happened is we everything started to melt slowly, and then we hit the Younger Dryas, where everything went into a deep freeze for a couple thousand years, and then everything melted very, very suddenly. Right.
Well, it started with a sudden melting.
Okay.
And that sudden melting was then followed by a more gradual melting, because meltwater pulse 1A was at 14,600 years ago.
Right.
So that was like the beginning. So there was a catastrophic beginning that involved rapid melting. Then from 14,000 to 12,900 years ago, the climate began to warm. And that warming is exactly what you would expect, let's say, from the astronomical influences that were identified, 100 to 150 years ago, that are usually called the Milankovitch forces, which is the changing geometric relation between the Earth and the Sun.
Okay.
The eccentricity of the orbit, the obliquity of the axis, these things, how much the axis is tilted, how is the sun farther away, is the Earth farther away from the Sun during its summer or winter? It's looking at these combinations of various influences, because you know yourself that if the sun is coming directly, like at the equator, the sun tends to come more, you would say, normal or at right angles to the surface of the Earth. As you get further away from the equator, the angle of the sun gets very low. And the lower the angle is to the horizon, the more atmosphere the sun's rays have to penetrate, and therefore there's more scattering, and therefore there's less surface warming. So when you have these various changing geometric relations between the Earth and the Sun, there is this gradual cooling and a gradual warming. At the end of the last ice age, there was a period that the three factors working together that produce this effect were such that you would expect to see a gradual, gentle warming. And we did. Now, the problem is that right at the beginning of that, and it may have actually started somewhat before 14,600 years ago, but at 14,600 years ago, there was a spasm of warming, because there was a spasm of melting, because there was a spasm of oceanic, sea level rise, right? Then, for the next, from 14,600, let's say, post meltwater pulse 1A, to 12,900 years ago, you had this gradual warming, gentle warming. Ice sheets are shrinking back, so that by the time in that interim, they maybe lost 15% of their total mass. Okay, maybe something in that ballpark. Which, of course, was also, as the ice sheet is shrinking back, it is releasing land. It's exposing new land. So as the ice is moving back in sort of normal gradualistic rates, forests are following in its wake, right? It makes sense. You would have boreal forests or northern forests that are following in its wake. And this is what you see. And then the Clovis culture shows up, and they also appear to be moving their settlements further north as the ice sheet is receding. But then we get to 12,900. At 12,900, there's a huge spasm of this within 1 year, this warming, this 1400 year period of warming, boom, it's over. And the planet lurches back in to what we considered the full glacial cold that you would find when you went back to 16, 17, 18,000 years ago, when the planet was at its coldest. So this was the Younger Dryas, the onset of the Younger Dryas. And it lasted about 12 to 1300 years, right? But the onset of the Younger Dryas was really catastrophic. And the Younger Dryas itself was a planetary cooling, a very extraordinary and extreme planetary cooling. Yet, right at the boundary, as the dating gets more and more precise, there was massive mega flood and melting events. So there had to have been some introduction, a huge amount of thermal energy into the system to trigger that melting, and then immediately followed by the Earth plunging back into full glacial cold, which lasted for 1,300 years. And then at the end of that, at 11,600, you had meltwater pulse 1b, and at that point, the planet was able. It was almost like that. It took that second blow to finally knock the planet out of the ice age, because after the 11,600 meltwater pulse, then basically the ice continued to disappear and shrink back, and 2,000 to 3,000 years later, it's mostly gone, and the planet begins to assume its present appearance.
Now, the Younger Dryas almost seems like a nuclear winter type of situation.
Yes, that's exactly right. It's exactly right, Seriah. It does. And yeah, and in fact, that comparison has actually been made.
Okay. Now, when we're talking ice ages, I mean, at the same time that we had these huge ice masses on Canada, we had Siberia, which was mostly ice-free, which is now covered, in permafrost. So do you think there was any kind of shift there? Like whatever caused the end of the ice age maybe shifted the axis a little bit?
Well, that's an interesting question. And, when I was really getting into catastrophism in the 70s, first starting to get into it, and I was reading, people who are considered somewhat fringe now, like Immanuel Velikovsky and Charles Hapgood, they both talked about axial shifts. Velikovsky talked about an axial shift, I believe, if I remember right, triggered by the close passage of either Mars or Venus.
Venus, I believe.
Venus, I believe, yes, which at the time I read it, I thought, I don't know about this. But, in the interim, nobody, I don't think, believes that Venus was, ejected from Jupiter, came by Earth, and somehow, because the physics are there's no way you can get the physics to support that whole scenario.
It's aside from the Jupiter part, it's still part of the electric universe belief.
Yeah, and that's where I start having trouble with the electric universe, because, I don't think you'd find a single astronomer or a single astrophysicist that would say that Venus, in the time of humans, and, at least for tens or hundreds of millions of years, that Venus was in some radically different orbit than what it's in right now.
Okay.
That could bring it within the vicinity of the Earth, which I presume is how you're going to explain the voltage potential that would allow the arcing to take place.
Right.
Yeah, I just, it's one of those things, you always, to me, Occam's razor, go for the simplest explanation. And we know, because we have witnessed, fragmented comets hitting planets.
Yeah.
Right? We see stuff coming out of the sky and hitting the Earth, and we collect the remnants of those pieces. We see, maybe once every month or two now, we see a flyby where something anywhere from a few dozen feet to 1,000 feet in diameter is passing through Earth's neighborhood, cosmic neighborhood. We are seeing more and more asteroids, in the vicinity of Earth's orbit, way more than anybody was imagining was there, 30, 40 years ago. So we know that these guys are out there in pretty large numbers. We know that they hit planets because we see them.
Right.
And we see craters on Earth, and we can do experiments where we can completely reproduce those craters by shooting projectiles into an appropriate matrix, right? Mm-hmm. So my thought is to me, that's something that you don't have to get so far out. You don't have to get so hypothetical with that, because and some of the electric universe people that I've talked to, they don't even consider impacts as part of the equation. Yeah. And I go, you can't just throw impacts out the window. I mean,
definitely not.
No, we've got 300 years now of pretty solid research supporting the idea that, planets do get impacted by stuff, particularly by, asteroids and the debris of disintegrating comets.
But if a comet were to hit the Earth, would it be enough to knock it off axis? I mean, why was like Lesser Antarctica and Siberia warmer during the Ice Age?
Well, that's one of the puzzles, and it certainly hosted enough biomass to support, millions of megafauna. Mm-hmm. Because some of the most prolific remains of megafauna are to be found, in the Siberian Arctic, frozen in the permafrost or washing up on shores, during storms and stuff of the Arctic Ocean. And that's where we kind of get to the ideas of Charles Hapgood, which to me are not quite as far out there as Velikovsky. And I will say this about Velikovsky. I see that his work was bimodal. That is, there were two parts to it. One, he collected together the evidence for catastrophic episodes in Earth history, such as it existed back in the 1950s. And so he did a very valuable job of archiving and collecting and collating that information. He also looked at, legends and mythology and so on, and saw that it was legitimate to make a connection between that and the other side of the equation, which was actually geological and paleontological evidence. Mm-hmm. So give him credit for that. The other part of it is now he documents the reality of catastrophism or catastrophes. Now the other part of his work is when he goes and attempts to explain. It comes up with what caused these catastrophes, and that's kind of where when you go and read the criticisms of them, I think in the early 70s there was a book that came out called "Scientists Confront Velikovsky." So shortly after I first read Velikovsky, which was 72, 73, 74, I was like, I don't know about this Venus idea. So I read the counterpart of that, and what I noticed was they basically ripped Velikovsky's astrophysics to shreds, but they didn't really touch his catastrophism, you see. So I came away from that thinking, well, the idea of catastrophes in Earth history and in human times is robust. Then Charles Hapgood's work, he did the work on the path of the poles. Now, he didn't assume that the entire axis of the Earth shifted. What he assumed, or his model, was that the crust of the Earth shifted with respect to the mantle. Right. Now, what's interesting is he came out with that idea at really about the same time that the Wagnerian continental drift plate tectonics model was finally being accepted by mainstream Earth science. See, only in his version, it happened a whole lot faster than in Wagner's version. So the question is there anything that could trigger the kind of accelerated crustal movement that Hapgood was invoking? Well, the answer is probably not, unless you had an impact. There have been a number of astrophysicists that have actually calculated the size of an impact that would be required to cause a shift of the Earth's axis, and it's big. I mean, you're talking about something, several hundred miles in diameter.
Right.
And we're not talking about something like that. We're talking about something that, on a lesser scale, let's say, for example, than the impact or impacts that terminated the dinosaur age 66 million years ago. So the question then becomes, can something trigger, because now mainstream science is accepting that, the crust of the Earth does move, right? Mm-hmm. Now, I've often thought over the last couple of decades that Okay, if you look at the planet as a whole, it spins on its axis. So it's, if you're standing on the equator, your movement is, you're going to be going relative, let's say, to the axis of the Earth as your datum point. You're going to be moving about 1,200 miles an hour, right? In order to make the whole, say, 26,000 roughly mile circuit around the equator of the Earth in 24 hours, right? And then, of course, as you get to the pole, the circle, the latitude circle gets smaller and smaller and smaller in radius, and so, of course, you don't have to be moving as fast to make to complete one circuit of a smaller circle.
Right.
But due to the fact that the Earth is not perfectly rigid, it's essentially plastic enough that as it spins on its axis, it bulges around the equator. And that equatorial bulge means that the equatorial diameter of the Earth is 26 miles greater than the polar diameter. So what that does, in effect, one consequence of that is that the equatorial bulge acts kind of as a flywheel that helps to stabilize the Earth's in its orbit, so that there's not random and chaotic motion of the Earth's axis, which would make it very, very difficult for higher life to evolve. And if that bulge did not exist, Seriah, you and I wouldn't be having this conversation right now.
Right.
Anyways, what that means is that there is a distribution of mass around the Earth's center of gravity, right, that is dependent upon its latitude. So if let's say you're at the center of the Earth and you want to dig your way to the surface, well, if you dig your way to the surface at the equator, you got an extra 13 miles to dig than if you're digging your way to either the North or the South Pole.
Right.
Another way of looking at this is that if you're starting a journey and you're at the equator and you travel to one of the poles, you've just gone downhill 13 miles. See? Okay, so now let's get to part two of this scenario that I'm describing. The Earth, again, being plastic, we know already, we can say with a high degree of confidence that, yes, things are moving laterally, right? That's continental drift. The things are moving laterally, right? What could be called into question is the rate at which this is happening. But now there's another type of Earth movement, and this is called isostatic movement. An isostatic movement is vertical. It's movement closer to or away from the Earth's center of mass. Now, how do you affect that? Well, for example, let's bring on an ice age. So now you start accumulating a whole lot of ice up on the continental landmass, right? When that ice is a mile thick or a mile and a half, maybe even 2 miles thick, that's a lot of weight.
Yeah.
You understand? That's a lot of weight. And guess what happens? The Earth sinks under that. And that is called isostatic depression. So the Earth sinks, right? It gets closer to the Earth's center of mass. Its surface sinks and moves closer to the center of mass by anywhere from 1,000 to 2,000 to 3,000 feet, right?
Yeah.
Now, what that means is that in normal circumstances, that 3,000 vertical distance would actually translate into a lateral distance. In other words, if you move, let me try this. If you're taking a spot on your surface and you want to move it 3,000 feet closer to the center of mass, well, you move it further away. You move it towards one of the poles, right? But what happens if it stays in the same place, but now it's 3,000 feet lower, right? So now what has to happen is there has to be a new equilibrium established when you've got a huge mass of ice like that weighs, I once calculated, I mean, we're talking about hundreds of trillions of billions of tons of ice. Wow. Right? Now, we rapidly melt that ice. And we suddenly take, in the geological sense, boom, in an eye blink, that ice is gone. And now you've got this massive isostatic depression over North America. And as soon as the ice is gone, in the analogy I always use is, think about you've got your comfortable chair or couch with a cushion on it, and you sit down on it. And as you're sitting, like I'm sitting on a chair right now with a nice comfortable cushion, and it's isostatically depressing. And when I stand up, when this conversation is over, it will isostatically readjust.
Right.
To not have a 250-pound guy sitting on it. So the Earth is doing the same thing. Well, now think about this. What happens when you suddenly remove all that ice and the surface of the ground begins rebounding, isostatic readjustment takes place. At the same time, all of this water, this weight is being transferred from the continents back into the ocean basins. So while there is an isostatic uplift taking place in any areas where the ice was located, there is a corresponding isostatic depression taking place in the ocean basins. Now, the floor of the ocean basin is crisscrossed by a whole lot of fault lines, the whole mid-Atlantic ridge, for example, is like a giant fault line, and it's transected by hundreds of what are called transform faults, right? Mm-hmm. What these faults do is they provide zones of least resistance, because they're basically, at the deep ocean is where the Earth's crust is the thinnest. It's mostly composed of basalt rather than granite, which forms the core of the continents. And so it reacts differently. Now, we see that since the removal of the ice, for example, if we were looking here, if we had visuals, I could show you photographs of Hudson's Bay, where you can barely clearly see shorelines that are 1,000 feet above present sea level. And that, of course, is due to the uplift. Okay, so here's what I'm getting into in a long roundabout way. When you have these large-scale shifts of surface mass, it would make sense that there has to be some type of an orbital response that is the Earth's effort to regain a new equilibrium.
Right.
So here now, you've got several million square miles of North America that's moving away from the center of mass. Well, now, if the Earth has been, has been in equilibrium state with the weight of the ice, now the ice is gone and the continent is moving away from the Earth's center of mass. Now there's a disparity between its distance from the center of the Earth and its latitude. You see where I'm going with this?
Yeah, definitely.
So it would seem like there would be a natural response for there to be a short-lived pulse of accelerated plate tectonics as the Earth is trying to readjust to this new, rapidly imposed distribution of mass. And I think that might be where we could kind of find a variation of the Hapgood model, is that there might be short-lived periods. And I think the seismic and volcanic response, which we know was significant, because the deglaciation process we should throw that in the mix too, was accompanied by very large-scale seismic events, maybe as much as 10, even possibly 11, but certainly as much as 10 on the Richter scale. 9.5, 10, a series of earthquakes, right? Because of this rapid redistribution. We also know, and it's turning out more and more evidence is being uncovered every year, that there was also a major volcanic response, which would only make sense.
Sure. And I think I remember Graham Hancock writing about how, like, there are places that do not have tectonic plates, like Scandinavia and stuff, that had just these weird rolls of rock, sort of like waves of rock that were because of the ice being removed from them, and the weight distribution changing.
I'm not recalling that from his book.
I'm trying to remember what he called them. But he said there are areas that don't have tectonic plates that you can still see the result of all the activity. That was, I think, in Underworld.
Okay, which is probably the one book I haven't read. I guess go ahead and get Graham on the line and let's ask him.
I wish.
Yeah. Hey, it could happen. Maybe not tonight, but...
You had mentioned something else that I was going to mention. Like places like in Canada and upper northern North America or northern United States, you're still seeing that rebound because it's still they measure it still coming back up from all that weight being removed from it.
Yes, very good point. They are. It's not it's not going as rapid now as it was in the first few millennia after the deglaciation, because you can actually look and notice that the strand lines or shorelines adjacent to Hudson Bay, there's a much greater distance between successive shorelines, early on, and then as the land rises, the shorelines get spaced closer together. So basically, because it's going slower. So the process is slowing down, but it's still happening. You're right.
Yeah, 12,000 years later.
Yeah.
Now, we were talking about.
Go ahead.
We were talking about the Finger Lakes too, and the scientific establishment says that the Finger Lakes, where I live, were carved out by glaciers. Moving slowly south and carving, these long Finger Lakes into New York State. But you're saying that they're more likely caused by flooding, not the glaciers themselves.
Correct. That is yes, and that's consistent with some of the evidence for rapid scouring and infilling that took place. See, the problem is that the assumption if they're scoured by, and don't get me wrong, the glaciers probably had an important role to play, but I would also say that that even more important than that was highly erosive subglacial floods emanating from an epicenter in the eastern Lake Ontario basin. And that came about as a result of studies that were conducted, core samples that were taken from the bottom of the Finger Lakes.
Okay.
Because what those core samples showed was you would expect that you would have multiple layers showing a whole succession of depositional events, right? So one of the things would be that you would find a layer of glacial till, which is the ground mass of that the glaciers produce when they are bulldozing their way across the land, right? And then you should have, depending on the age, you should have successive layers. I mean, if those were lakes, and those lakes existed, let's say prior to the end of the last ice age, you should find evidence of those earlier, for example, let's say that those lakes were there 30,000 years ago, or 25,000. Let's go 25,000 years ago. The ice wasn't there, right? Now, the ice essentially reached, if you look at a map of the Finger Lakes, you'll see that the ice essentially reached the southern limits of those lakes.
Right.
So those lakes were basically, they were under the ice, but they were right at the margin of the ice where the ice was beginning to thin out. And right when you get like to the bottom, like down there where Watkins Glen Gorge is, at Lake Seneca, right there, that was sort of the end of, that was where the glacier terminated, right?
I thought the glacier reached all the way down to it helped form Long Island.
East of here it did. There was, but this we have to picture that it wasn't a uniform. Marginal position. This was like a lobe here, right there. In fact, I think the lobe. Let's see. It's probably, I know it's where 81 crosses. I forget what state highway. Right there, kind of marks the picture almost like a tongue-shaped lobe that came down. And reached over so that, where Niagara Falls now was under the ice. And then there was another lobe of ice that came down and created Long Island.
Okay.
But they were they were ultimately part of the Laurentide ice sheet. But you have to picture that the margin of the ice sheet had a whole series of extended areas, lobate areas, you would call them, like tongues of ice. So it was almost like it wasn't a smooth, continuous. That's what I'm trying to say.
Yeah, it wasn't a straight line across.
Topography, because you get to the Allegheny Mountains, which are just south of the Finger Lakes, and that sort of acted as a terminus. There were mountain glaciers over those mountains, but you have to picture that the Laurentide ice sheet, which was the big mass of ice that came out of Canada, crossed what is now Lake Ontario And then where like Rochester, New York is now, that was under the ice, and it pushed as far south as, and sort of buttressed right up against the northernmost part of the Adirondack or Allegheny Mountains. So the Finger Lakes were under the ice sheet. Okay, so now here's the thing. When they took the core samples, and this was back in the 90s, what they discovered was that the sedimentary infill, and some of the lakes were enormously deep. Enormously deep. And the infill was basically massive, and it was directly on bedrock. So what that means is a massive infill. It was not a layered infill. There was no strata to it like you would expect, if there was a long succession of lakes there. What you would assume is that if those lakes pre-existed the late glacial maximum, if they were there, you would have then as the ice encroached, the lakes would freeze over, and presumably the question is would the ice now move into the pre-existing lake basins, or would it move over the lake basins, and you would actually have the existent lakes under the ice sheets? Well, if you had that case, then you would have had a continuous succession of deposition that would have been coarser during the glacial periods and finer during the interglacial periods. But that's not, you don't find that kind of succession of strata in the lake, sedimentary. You don't find laminations, any of that. What you find, except when you look over the last roughly 10,000 years, then what you're seeing is that there is like normal deposition, which is because every year when you have lakes, during the summer, it rains, the water flows into the lakes, and it carries sediment with it. That sediment could be sandy, it could be silty, it's going to have pollen in it, it's going to have organic remains. During the spring, especially during runoff, there's going to be a big flush of material so that the sedimentary layers become what's called, so that there's a heavier, more coarse layer that forms the bottom, because that's the spring runoff. And then as the summer proceeds, it gets finer and finer. And then when winter comes, basically the deposition of this material, the influx of this material into the lake stops. And then when spring comes, you have another layer. And so you get this buildup of these layers.
Right.
So you don't find that. That's what I'm getting at. You don't find that in the Finger Lakes. What you find in the Finger Lakes is that there's hundreds and hundreds of feet thick, massive, bouldery, chaotic sediments sitting right on bedrock. So what does that mean? Well, then you got to ask the question, how did the glaciers do that? So since this is near the glacier margin, the glaciers themselves are getting thin at that point. They're not a mile and a half thick there. They're, basically a couple of thousand feet, maybe maximum, up in the area of Lake Ontario, thinning out to essentially nothing or a few hundred feet at the southern terminus. So how are they gouging out, troughs into bedrock that are 2,000 feet deep?
Right.
See, that's where the problem comes in. And when you've got this massive infill of sediment, that looks like and then the sediment, as they find and they date organic remains, they're not finding anything older than about 14,000 years. And see, if this had been a lake for any length of time, you should be able to pull out leaves and twigs or pollen or something, bones, something that could be radiocarbon dated.
Yeah.
And no, they're not finding that. So what it looks like is that over a very short period of time, the troughs were excavated down deep into bedrock, and then the final act, once they were excavated, then they were dumped with a huge amount of bouldery, chaotic infill. So where does that leave us? Well, I think where that leaves us is basically we're looking at very powerful subglacial floods, just producing. See, if you go and you look at say the coulees of eastern Washington, they're basically, Lake Seneca is about the size of Grand Coulee that I was talking about earlier.
Right.
If you took Lake Seneca, took the water out of it, and moved that entire topographical configuration and set it down in eastern Washington, people would call it a coulee. except that it's, in a completely different, out there you got 15 inches of rainfall a year, and Western New York, I think, is 45 to 50 inches of rainfall, and you've got lots of vegetation, and so you've got a completely different environment. But basically what you got is the same thing. You've got this very deep bedrock trough that's been eroded into the bedrock. It's now filled. To me, one of the closest analogs to the Finger Lakes is some of the elongated, you could call them Finger Lakes of the Canadian Rockies, like Lake Okanagan. I think is a very close analog to the larger Finger Lakes. And there you find the same exact thing. You find deep scoured bedrock troughs with massive infill.
So where did they empty out? Just into the southern tier area?
Well, in the case of the Finger Lakes, I think what happened is the water it emanated from the eastern basin of Lake Ontario, which is, and if you actually look at a map of the Finger Lakes, you'll notice that their axes tend to be radial.
Yeah.
And if you draw those axes, they converge on the basin of eastern Ontario. And then you look at the floor of Lake Ontario in that basin, and it's massively covered with these enormous drumlin field, which is then also found in the zone between the southern shore of Lake Ontario and the northern, the mouths of the Finger Lakes, basically like at the northern end of the Finger Lakes. You got a massive drumlin field in there with thousands of drumlins. It's quite extraordinary. And again, if we had visuals, I would pull up and show you some photographs of these. But it brings us back to what you and I were talking about before the show, which is one of the things I've been obsessing over recently is drumlins. And
explain to people what a drumlin is.
A drumlin is basically a hill, but it's not just a random hill. It's a hill that has a very distinct morphology. And they're always associated with glaciers because of the fact that they're only found in areas that were covered by glaciers, right? They're not found in areas that were not covered by glaciers, but they are streamlined, and they typically have a blunt end and a long tapered end. And they can be anywhere from a few dozen feet high to 200 or 300, 400 feet in thickness, just depending. So here's what you have to picture, is that as the ice is moving over the land, it's grinding the surface of the earth, right? Yeah. Pulverizing it and just churning it. And so it creates these thick layers of glacial till. It's called till, T-I-L-L. When the ice recedes, that's one of the clear indicators that there was a massive amount of ice there. You simply look at this torn up, churned up, chaotic ground mass filled with, boulders and cobbles and gravel and sand and silt and organic material all jumbled and mixed together with no structure or no order, and that's glacial till. Unlike material that is put in place by water, which has structure to it. Water creates the structure within its depositional mass. Ice does not, except with the exception of drumlins, or so the theory goes. And this is for 150 years, geologists have been struggling, I would say, to explain drumlins as the consequence of the glaciers moving over the ground. And they have not been able to really come up with anything that anybody agrees upon. Now bring the late John Shaw, Canadian geologist, into the mix in the late 1980s and 90s. And he is proposing that, no, they were associated with the glaciers because they were under the glaciers, but they weren't formed directly by the glaciers. They were formed by water moving under the glaciers. But not just water like we know that from modern day glaciers, you will see water moving under the glaciers and discharging at the glacier margin. But we're talking about water that's very large amounts of water moving under extreme pressure. So he came up with a model of subglacial floods to create drumlins. So now it's a two-step process. First of all, the glaciers come in and grind up the land, and turn it into glacial till. Now you have these highly pressurized subglacial floods moving under the ice sheet. And what it's doing is it's taking that till and it's shaping it into streamlined forms, aerodynamic type forms, or fluviodynamic in this case, as just in the same way that, because what it's doing is the water, whenever it is eroding something, whatever it is, and the rate of erosion is going to be directly dependent upon the degree of resistance of whatever it is that the water is encountering.
Right.
But let's say you've got something that's relatively resistant, but also relatively erodible, like maybe a soft sandstone. Okay. You got a soft boulder there, and the water is flowing against it. And let's say you quarry this boulder right out of the ground, and it's a nice cube sitting there with sharp corners. Well, the first thing the water does is it begins to round off those corners and the edges. And it's the same way that, when you see rocks in rivers, that are, some of them are almost perfectly round, right? That's because they've been rolled and tumbled in the water. It knocks the corners off. It smooths off the angles. It's basically, so now if you have an obstruction that's you've got a water flow and it meets an obstruction, the water will go to work on that obstruction and begin changing its shape so that shape provides the least amount of resistance to the water, right? It's trying to, create this form that has the least amount of friction. So think of a boat, a canoe, any watercraft, how it's designed. The hull of a boat or a canoe is designed in such a way that it's reducing the frictional drag of the boat or the canoe through the water, right? Obviously, if you had a square prow on a canoe, you'd quickly discover the difference that the aerodynamic shaping does, right? Because you go, oh man, this is ridiculous, trying to paddle a canoe with a square prow. But once you streamline it, then it's moving through the water with least resistance. So it works both ways. So what happens is when the water flows, it meets an obstacle, it wants to shape that obstacle aerodynamically or fluviodynamically, more correct, I guess, to provide the minimal amount of frictional resistance to the flow of the water. This is what we see in drumlins. We see hills that are aerodynamically shaped. They duplicate an aerofoil that is, because air, of course, air is a fluid, just like water. And so the same principles apply, if you're designing an airplane wing. Think of an airplane wing in cross section. It's designed to minimize the frictional drag. Well, this was what John Shaw saw in the case of the drumlins. He says, well, they're aerodynamically shaped. They're exactly what you would predict if the flowing water encountered, let's say, a mound of stuff, and it wanted to reshape that mound to minimize the frictional drag. This is what the end result would look like. Well, then he went further and he began to look at some of the internal, where some of the internal structure or architecture of the drumlins was exposed. And what do you suppose he found? He found that there was sorting. Remember I said that only water will sort things? Picture this, you've got a flood and you've got flowing water. And during the flood, the water, let's say in a creek or a river, is moving faster. It's more voluminous than normal. And so in floods, you have a lot of sediment transport, right? And if you look at the sediment transport, that can be an indication of how intense the flood is, right? The magnitude of the flood. Because, for example, out west in some of these floods, you will see boulders that were 10 feet in diameter. Now, obviously, it takes a much bigger flow of water to transport a boulder 10 feet in diameter than to pick up a pebble an inch or two in diameter, or even, in modern floods, you'll typically see, stones being moved that are, several inches, up 6 inches in diameter. That's not unusual, right?
Right.
So obviously, the greater the flow, the more intense the flow, the greater the magnitude of the flow, the larger the sedimentary load is going to be, and the more stuff there's going to be. Well, the competency of this moving water to carry this stuff is going to be dependent upon its velocity. So if the velocity of this water slows down, it starts depositing its sedimentary load. Well, what is it going to deposit first?
The big stuff.
The big stuff, right. So here's how water, there's just one example of how water will sort things. And in some of the tours that I do, I show, they're called boulder trains that extend, let's say, off the lee of prominences into a river valley. And there's a boulder train. It might be a mile long. And at one end of it, you see boulders that are 2, 3, 4, 5, 6, 10 feet in diameter. And then as you go in one direction, you'll see that the boulder sizes get smaller and smaller, and the proportion of finer grain sediment increases, and you get to the end, and it's a much different character of sediment. So from that, you can determine which direction the flow was, because obviously the upcurrent end has the biggest material and it gets finer downflow. So you call that a paleo current indicator. But that's an example of how water sorts material. It also, because water moves typically in a pulsed fashion, particularly during floods, it creates a visible stratigraphy, right? Whereas in glacial till, you don't have that. So to make a long story short, what John Shaw discovered was a lot of the drumlins, to which he had access to the internal structure, saw that there was these various kinds of sorting. So between the streamlined forms and the internal architecture of the drumlins, he concluded that they were shaped by water. Now, the geological community was not ready to endorse that theory. And even though it made perfect sense, in a limited scale, here's the problem. The drumlin fields associated with the late glacial period are so vast that the floods implied were just too much for mainstream geologists trained in, gradualist models and so on to even begin to wrap their heads around. And so they basically said, the floods that you would require are on such a scale that we can't even imagine it. So therefore, they didn't happen that way. So those are drumlins. Anybody can look up a drumlin online. You'll probably get some variation on the standard explanation, which, if you're going, like in my recent podcast, Cosmographia, we've been talking about drumlins a lot. And we had Jerome Lessman on a couple of episodes ago, and I think that episode is just being posted now. But Jerome Lessman was a graduate student under John Shaw, and he co-authored a paper with John Shaw in the year 1999 that was a very seminal paper. Probably the importance of that paper is beyond what we would be able to discuss tonight. But the background is simply it connected, what it did was it connected drumlin formation with this massive flooding out in eastern Washington, the so-called Channel Scabland, Lake Missoula megafloods, and surmised that the source of some of those floods, at least, was up in Canada. And this was a major paradigm shift in terms of the dominant paradigms as to explaining those particular megafloods. The ones that, for example, I used the earlier example of Grand Coulee out in eastern Washington, which would have been produced by that particular series of floods. So, anyways, we had Jerome Lessman. My friend and colleague Brad Young and I spent 4 days out in the field with him. I think it was in 2017 in October, going up exploring the drumlin fields of British Columbia, because with the idea that those particular drumlin fields are associated with the massive flooding in eastern Washington. And what we found up there confirms, and we were looking for certain things, and we found them, and we documented them. We're talking about this episode that's going up on Cosmographia. Jerome comes on there, and he's explaining the whole process of drumlin formation and how we know that they're produced by subglacial water flows rather than directly by direct glacial action on the substrate. And it's interesting stuff, Seriah.
Definitely.
Because what it does is it basically extends the range of these dynamic giant floods to a scale that's, well, let me put it, hard to even imagine.
Yeah, easily. We're almost out of time.
Okay.
So if we go back to the first thing I asked you, what do you think? So you as you said, you think there's multiple events. Do you think they were all comet related that caused the end of the ice age?
Well, comet related, yes, but I'll qualify that. See, to my knowledge, there are no impact proxies at 14,600 like there is at 12,900. At the layer of the black mat, they have found nanodiamonds, abundant nanodiamonds, which are only produced under extreme conditions of heat and pressure. Right? They can be produced in the laboratory, but where they had been actually initially discovered was in the aftermath of nuclear weapon testing in the deserts, like in the aftermath of Trinity. They found nanodiamonds. Right? They've also found nanodiamonds associated with the Cretaceous Tertiary boundary that we know was associated with a great impact, at least one impact in the Yucatan Peninsula. And there's a layer of nanodiamonds associated with the mass extinction episode of the dinosaurs in the Cretaceous Tertiary boundary event. And those nanodiamonds are almost indistinguishable from the nanodiamonds found at the Younger Dryas boundary. Magnetic grains. There's been an iridium spike identified, an enormous iridium spike identified in the Greenland ice, right at the 12,900. So there's a whole series of impact proxies associated with the 12,900 event. At this point, there is no knowledge that I'm aware of at this point, studies showing impact proxies at 14.6 or at 11.6, which were the other two great meltwater pulses. So what triggered those? Well, one thing is that if there was an impact at 14.6, maybe that layer got obscured by subsequent events. But there's something else again that we're not going to have time to get into tonight, but this is the discovery of the the family of Kreutz sun-grazing comets, and the connection between the infall of cometary mass into the sun and the coronal response of the sun to the infall of that mass. And it seems like with our sun-observing satellites now operational, what we're seeing is that would suggest that the infall of a large amount of cometary mass into the sun could trigger a substantial solar response. I'll just leave it at that.
Okay, so kind of going in the direction of Robert Schoch's idea.
Yes. See, I don't see a contradiction between Robert Schoch's idea and the idea of an impact.
Yeah.
In fact, I presented this at a conference a couple of years ago that Robert was at, and I hope he's considered the possibility that what we're actually looking at here could be like a solar system-wide event,
right? That
involved maybe even multiple impacts on the Earth and a very significant solar response, and a hyperactive sun for a very short period of time that could have, been responsible for a large number of, like, let's say, a pulse of coronal mass ejections or proton storms, and that could have affected the Earth. So I think that's how we need to be thinking. It's not. I don't think it comes down to an either or.
No,
it's
neither
either
do
an
I.
impact or it's the sun. I don't think that at all.
All right. Once again, we should stress you are no longer associated with Sacred Geometry International.
Thank you.
You can be found at randallcarlson.com. Cosmographia is the new podcast with the Snake Brothers.
Yeah, great guys. And
and that's with a K.
Randallcarlson.com is going to get you to everywhere you need to be.
All right.
And there will be a lot of new content presented there in the very near future.
Awesome. All right.
Yeah,
we'll have to have you back soon so we can continue this conversation.
You know what, Seriah? I love this kind of conversation. I don't know why, but I just...
So do I. All right. Thank you, Randall.
Thanks for having me, Seriah.
I want to take a moment here to give a shout out to all my patrons. All of you help make this show possible. I want to give a special shout out to those of you pledging $10 or more: Frank Earl, Nagatha Christie, Patricia W., Barbara Fisher, Will Powell, Big Boy Limina, Craig Parmenter, Walker, Joanna Rojas, Maddie, David Moore, Vincent Trewill, The Great Change, Sam Sharon, Stone Wilderness, Luke Osborne, Becky Trainer, Rob Drummond, Alex Whitcomb, Edu Camahort, Tactical Therapist, Janet Bunderson, 36 Dingo, Taylor, Jennifer Campbell, American Rambler, Kevin, Matthew Sproul, John Rutledge Foster, Eric Citron, Andy McNamara, Sasha Jorg, Matthias Sunby, Dominic O'Malley, Christopher Vaughn, Super Inframan, Riker and Stark, Tim, J. Otto Bullitt, Kevin Shrek, Jose A., Roger Gonzalez, Craig Cicernos, Ray Benedetto, Linz Jackson K., Ellison Cook, Alfred Tuttle, James Lattimore, Patricia Giaquinta, William Lovelace, Mark Brady, and Carla Mahoney. Thank you so much for helping make this show possible. I hope you enjoyed that conversation with Randall. There's a Patreon-only segment with him where we talk about the mysteries of the moon. And that'll be up later this week for Patreons. And if you want to become a Patreon, go to wheredidtheroadgo.com and click on the link for Patreon. It's only $3 a month. You get a bunch of extra content every month, and it helps us keep this show going. Also, Randall wanted me to add in here that not only is he not associated with Sacred Geometry International anymore, but the classes being offered there, although they are him, he is not seeing any money from that. So he asks people to stay away from that and his research that is posted there and only go to his current website, randallcarlson.com. See you next time. You have been listening to Where Did the Road Go? This show is made possible in part from our Patreons, and we thank you and everyone listening for helping us continue this exploration of the strange. You can always find everything Where Did the Road Go related at www.wheredidtheroadgo.com. And thank you so much for your support.